I'm going to talk a little bit about PSRI and strategic partnership with CPFD. I think we known, CPFD, we originally started interacting back in 2006, right? And we go back to the founding fathers of CPFD, Dale, Bill, we interacted with them way in the early stage and evolution of the software, and we use it through this strategic partnership. We use it internally at PSRI as well, and lately especially Sam is really working closely with us. And how do we use it? I kind of elaborate. Mainly the topic here is fluidized beds and its applications, right? Been used for since what? 1926, right? Original gasifier in Germany. And then we came a long way. Still, do you think we know a lot about fluidized beds or particle technology? There's a lot we don't know than what we actually know today, right? I'm going to make that case and how we are applying. If you assume that because we've been using this technology for so long, and I know how to design certain processes, now I'm moving into new energy paradigm shift here, emerging technologies. Can I just simply go ahead and design it and maybe use the tools like CPFD or other kinds of software without like saying, okay, Reddy has a certain personality and Rajat has a different personality. Because I know Reddy so well, Rajat would just be, he's also president. He's going to behave just very similar to that. Not true, especially particles. Particles, every particle has its own personality. You need to understand that not only in the CFD, but in the real world. So I'm going to make that case. It's very important to have that both experiments and modeling goes in tandem, in synergy. Right? So I just first, PSRI is an industrial consortium. Currently, we have about 37 member companies. Out of those, about 10 plus members are from these new emerging technologies. Right? Originally, the membership was mostly oil refining, FCC technology, combustors. Those are the technologies. Now, it's going into newer technology. The main vision is PSI will be the first. If you're developing a new process, what we like to think is PSI is the first place you stop. Okay? Engage discuss with PSRI, we can help. We have that 50 plus years of experience dealing with these. PSRI will offer about, say, 4 buckets of service here. Original mandate for PSI is a membership research. Right? These oil companies, remember the Second World War kicked off this whole oil refining, scaling up these processes, and so on. It took them almost another 30 years, 1970s, to realize, why are we researching in our own laboratories? We have the same common issue when the Standard Oil split up into different companies. Why don't we pool the money and resources to do the R&D and understand to solve the industrial problems? That's the foundation of PSRI back in 1971. So we've been around for 50 plus years, right? And that's our still today mandate. So we work on common problems and we share the information to the member companies. Now, over that 50 plus years, we amassed a large amount of database, right? They talked about data science, database. For anything AI, you need your AI is as good as anything neural networks, anything that you're analyzing is as good as your database, right? So that's where PSRI strengths are. So now we're utilizing that. The other buckets are the contract research. We actually have a great asset, experimental setups. If he ever happens to pass by Chicago, we are right in Chicago. We have a great facilities right close to Midway Airport. So those units are available. So if you're developing a process and I want to understand something about that unit operation, we can simulate experimental data to validate these codes. It's a very, very important step. That is the contract research. And if you want to utilize the expertise that we developed over the 50 plus years, the way to take advantage of is the consulting. Consulting is a third way. So for us right now to engage PSRI is actually gateway. Consulting is a gateway into PSRI, and we firmly believe in this. We firmly believe in conveying that know-how at PSRI to the next generation, to the practicing engineers out there actually executing the real-world issues, right? So we do training. That's in high demand lately because there's so many processes that are coming up now beyond the FCC and known other technologies. And that's where a lot of training that's going on. We've been offering quite a course. So those are the offerings at PSRI. I'll give you those blue companies. That's something. If you are working with particle technology today, I can tell you you've got a job guarantee for the next 50 years. I'll make the case why. Because FCC technology has been the granddaddy. I mean, basically, after all this particle technology dominated the arena for the last 90 years, right? And I'll make that case in a few slides. And so it attracted all that resources, the manpower, the engineering power, all the power into that arena. Now we are on the verge of shifting energy paradigm, going into renewables, sustainable technologies, right? And it shows in our membership. This is a leading indicator after what's coming up in the pipeline. So these new companies, we still have, of course, doesn't mean that it's the end of the FCC technology. FCC is going to continue for a long time, but there is a shift into this new energy field. There are new companies that are getting into this arena and making things. That's what I'm going to make a case. Why the fluidized bed is going to play a major role in these technologies, right? And here is the process. When you talk about particle technology, here's a list of things that PSRI has been working for the last 50 years. Here are the processes that actually out there in terms of utilizing some of these. The one that I put in a bold face are the new emerging technology. There's a lot of interest right now. There's so much activity going on in those areas, and we can't find the right enough folks in the background to be able to work on these projects because when you go to hire an engineer, chemical engineer in the US today or in North America, probably they get exposure of 1 hour of training in their, on the fly in a fluid mechanics class. So you need to train these folks. And then, and also what's happening is there are very few academia working in this field. And there are folks in the industry, they don't want to lose those resources. They are already preoccupied. So we have a resource-constrained scenario in the US right now, not only in the US, all over the world, right? That's where PSRI is filling a role. So these technology development requires a lot of resources. I know they're talking about AI to speed up the process, scale up our process. Average in chemical engineering process to go from lab scale to commercial scale takes about 7 to 8, 9, 10 years. Yeah, you can speed up. You're not going to speed up down to 2 years. It's not going to happen in chemical engineering. It might happen elsewhere. So the folks that are working in this arena are trying to compress that development cycle into a short period. You can do that, but there are certain critical steps you cannot skip. That's what I'm going to talk about. So what are the areas that we're talking about? Lithium, battery materials, that means graphenes, electrodes. Renewables, biomass. Biomass is a low-energy particle. And you need a lot of issues with the transportation. Issues with how do you produce a biomass pyrolysis, biomass gasification, using fluidized beds. And this is direct and indirect CO2 capture, right? And also chemical looping not in the sense of capturing CO2 out of a flue gas. That's never going to be economical. But capturing CO2 in the context of production of hydrogen economy makes perfect sense, and you will see it's going to happen next 5, 10 years. A lot more effects, right? And then, of course, polycrystalline silicon. Remember, solar panels are expensive. Only 7, 8 years ago, tremendously expensive. Only maybe top 10% of the population can afford. Today, I make a case at least 60, 70% of folks can afford. Why? What's the difference? Thanks to fluidized bed, right? Fluidized beds historically has done this over and over again. It did it with FCC technology. Through FCC technology, made it, you can buy a car, but it's expensive to buy a fuel to put into the car. FCC technology did that, make that commodity, make it cheaper through the economy of scale. So common folk can buy that gasoline, diesel, made it happen. And same thing will happen to these technologies, right? And again, of course, mineral solid waste, dehydrogenation is another chemistry that's going to be a lot of interest in the future. You will see it. There's a lot going on, right? So I'll take one example, transportation, because a lot of people are talking about FCC simulations and so on. Well, today, there are 1.5 billion passenger cars in the world, just the passenger cars. So what is fueling those passenger cars, the planes, the heavy equipment, heavy vehicles? There are 825 active refineries in the world that are actually fueling these, right? That means how much they're consuming. They're consuming over 100 million barrels a day in the world, right? Out of that, US is consuming about 20 million barrels a day, on average, approximately, right? So that kind of energy need to be, if we're going to be electrifying the transportation, we need to, with next 30, 40, 50, 60 years, we need to come up with a substitution of that kind of energy through some other, if you're going to be electric cars, those battery materials, who's going to make that battery materials to produce that kind of thing, right? Think the scale. In 2023, I'm just going to talk about only US for now, and then you can imagine what would be the worldwide ways. There are 15.5 million light vehicles were sold in 2023. Out of those, almost 1.5 million vehicles are pure electric, not hybrid. That means already a 10% penetration into the new car sales, right? 10%, keep that in mind. Look back any decent article, any review articles, even the investment folks wrote all kinds of articles on this energy paradigm shift. They were completely wrong. They were predicting under 1% by 2030, on average. And it happened by 2023, already 10% penetration, right? What does that mean? That means that it's happening. Of course, it's slowed down now, but if you follow the Iceland example, it's going to pick up. It's all about the comfort level and so on. It's happening faster than people expected, right? All right. So, let's take example. How long it took FCC to evolve? I'm not going to go through the whole thing, but you can see the steps involved. To me, the two greatest things that happened in FCC. The invention of the zeolite structure. That's what the chemical engineers come up with, the miracle particle. What is the second greatest thing that happened in FCC? That side-by-side two vessels, be able to circulate that catalyst at an incredible rates. What are the rates that are circulating around that loop? Almost like 100 to 150 tons of material every minute. Do you see any mechanical pump in there that's moving the powder around? Liquid's easy. Gas easy. Particles, by nature, hey, they are pile of dirt, right? How do you move the powder around at 150 tons a minute? That's the beauty of these engineering companies, the marvels, that's where. So that circulation is what makes the magic happens. FCC, right? So those are the things we know. We mastered it. We rely on, companies like Technips, KBRs, UOPs, Exxon, of course, ExxonMobil leading the Standard Oil. They solve those problems along with PSRI, playing role side by side, understanding the physics behind it, and making that hardware reliable all the time, right? So if that's what's happening, let's translate it. If you're converting this into electrifying this transportation, right? Let's take some numbers, few numbers just to look. So on average, today we are about 10% of the sales are electric cars in the US. In the EV battery, each car battery weighs about 480 kilos. Out of that, about 8 kilograms of lithium is needed. And look at other metals. Cobalt, manganese. Where do you think that's coming from? Nickel. You start seeing the role of the fluidized beds, right? Especially lithium. So if that means if I need 8 kilograms per car, and in 2023, 1.4 million cars were sold in the US, that means we need about almost like 11,000 metric tons of lithium per year. And if you look at the scale up, imagine today is only 10% of the current sales, but not the whole fleet. What has to scale from here to ultimately to that level of 2 billion cars in the world in the future, next to say 4 or 5 decades, right? You need a tremendous scale up, right? So there's a great growth curve for any of these battery materials. And current process that they're doing today, they are not scalable to meet this requirement. They need to move away, just like when they went from a solid-state electronic semiconductor chip, silicon, to solar panel silicon chip. Silicon, there are less purity. This is a batch process. This is a fluidized bed process. There is no comparison. That's why the solar panels price came down. Fluidized made it possible to have economy of scale. That's what that thing happened, right? Same thing will happen here. You will see it's just a matter of time. The history taught us anything about the particle handling. So what is the exact role of the fluidized bed? Of course, we can't talk about that. It's IP, as every company has their own way of approaching these, right? But what does history tell us? Fluidized beds will play a role in every one of these processes, right? All right. I'm just going to, that's an example of one case example. We can go on, but I'm going to take few examples to show. Here's the gasification process, right? Well, coal gasification has been around for half a century, more than that, right? Only difference is today, people want more hydrogen economy, right? So it could be, or also, nobody wants to use coal. Coal is a dirty word now in the context of low carbon footprint, right? So it's people all want to do mostly biomass, maybe plastic recycle, municipal solid waste. That's where the current interest is, right? So it's a gasification, and then ideally, ultimately, you want to get is the hydrogen. But the role is the fluidized bed is going to play a major role at the part of that process. Not only here, even in the downstream areas as well, right? It makes sense. Fluidized bed takes it. Because fluidized beds are for chemical engineers, it's a perfect CSTR. Well-mixed system. It can handle wide range of temperatures. Because of well-mixed system, packed beds are very hard to deal with because you can have hot spots. But fluidized beds are very isothermal. I can run at 400 degrees C, I can run at 1,000 degrees C. I can run at 1,500 degrees C. So it's a very versatile fluidized bed reactor. It's hard to beat. If you start the cement industry today, they would not use rotary kiln, okay? Some things will stuck in each industry. But based on the merit, fluidized beds will win out today. If you start from the scratch, from a clean sheet of paper, right? You're waste because calcination, that chemistry wanted plug flow reactor. Rotary kiln is a very easy thing to do. Those days, everything mechanics, so much demand. So that developed and that's stuck in that industry. But you can make fluidized bed as a plug flow reactor. There are ways to do it. But that's solved. That's been solved. That worked. But the new industry, the fluidized beds will be the first one they consider before they consider some other unit operations. Okay? You will see this. All right. Biomass gasification, there's tremendous efforts going on out there, right? And it can be, so one of the challenging aspect is these reactors are not anymore, FCC is somewhere around 1-2 bar pressure. Some of these fluidized beds going to be in the future, some of these hard ones are much higher, like polyethylene reactors are fluidized beds, 25 bar. It's going to be in that kind of magnitude, 10, 20, 30, 40 bar pressures, right? So in those, the physics, we know a lot about group A powders. So much work has been done, a lot of understanding. When you move away more into B, that's a big unknown. Go into group C powders, cohesive powders, not well understood, right? You can throw in the CFD and say, okay, the CFDs will handle, but you need that validation step associated with that. So they go in tandem. You need that experimental data. You need that CFD modeling, simulation to validate the thing along. I'll talk about that. So the idea is these fluidized beds allow you to go to the higher pressures, be able to keep that well-mixed system, and so that it's a very versatile unit operation for these new technologies. Right? Pyrolysis. Of course, there's tremendous efforts going on. PSRI has been involved in all these processes I'm talking about. They put a lot of energy into this arena, especially biomass pyrolysis. There are several pathways. And in one of the pathways, of course, it's been publicly known, like I² process, for example, GTI and Shell had put in a lot of energy into it. I think it's made a tremendous progress. And fluidized bed plays a major role in that. Right? And low carbon hydrogen technology. This is another area that's going to be tremendous efforts. We got, especially in the US or any country that has an lot of natural gas. You take a natural gas, CH4, and you want to split that molecule into carbon and hydrogen. Right? Some people want hydrogen as a product. Some people want carbon as a product, because carbon is, depending on the pathway you split that molecule, you can get carbon in a graphene form, well-structured layered carbon. That gives you, right now, I have a Tesla. When I on a road, if I want to charge it, you pull into supercharger, you plug it in, it takes 25 minutes to get it to 80% charge. What is the bottleneck? Why not do it in 2 minutes? It's the electrodes. That's the bottleneck. If you can replace the current graphite electrodes with the graphene electrodes, and the right kind of graphene electrode, they're showing it, you can do it in about 2 minutes. Right? Because of that reason, they're throwing a lot of money into this development. And the idea is, how do you split that methane? Right? That's one aspect of it. We've been involved in several clients doing different things. Clearly, can't talk about, but that's context is the same, right? And this is a low carbon hydrogen technology, for example. We've been involved since 2000. This is with Professor L.S. Fan at Ohio State. He actually pioneered this idea along with a lot of efforts in Europe, but mostly in the US. It's L.S. Fan. The idea is, this is a chemical looping. That means you take a metal, you oxidize by combusting its oxygen into metal oxide, and you take the metal oxide into your actual reactor, process reactor, where it gives out the oxygen, pure oxygen without having to worry about nitrogen, right? So that is the concept. You circulate this around reduction and oxidation step here. But the concept in the context of absorbing CO2 doesn't make any sense. But it makes sense if you're trying to produce hydrogen. It makes perfect sense, and that's going to happen very soon. Not very soon, it's actually going to break the ground very soon. Right? So the idea is this kind of technology, that kind of loop, you can use any one of these feedstocks, and ultimate goal is to produce hydrogen economy. Right? And so this process is going to happen. Babcock and Wilcox is announced, that's the slide came from. We've been working with them from the last 5-6 years. So this is actually, they're going to break the ground next year on the first plant. If that's successful, they're planning more like tens, and initially at least they're planning like 30, 40, 50 kind of scale units, right? So there's a lot going on in the application of fluidized beds, both in this new hydrogen economy, in the electrification of transportation, and also it's in the splitting that methane to produce a graphene nanocarbon tubes on the carbon. Carbon doesn't have to be always graphene. It can be nanocarbon tubes. That is part of the structural light material for you. So there's a lot going on in application of fluidized bed. It's never been a better time for, I guess if you're working with particle technology, there's going to be exciting times coming up in the future. And of course, PSRI is going to be there playing a pivotal role at the center of those. And CPFD is going to play a role at the very closer, because the difference between other codes and CPFD, they focused on the particles, granular particles. Right? Of course, there's a DEM, but there's a ways to go, because there's a limit on how much you can scale to and how many particles you can simulate. I think CPFD, sometimes you want to put an engineering hat. That's what to me is a CPFD. They took, made some, this parcel concept, and so on, be able to accentuate, be able to speed up the computations along with GPU usage, be able to come up with a reasonable answer to a problem in a commercial scale. That is the beauty of the CPFD, right? And that requires, I'm stressing, what I'm missing in here is the presenting results. How do you know those results are correct? You want to put some efforts in validating those results, at least at some limiting step. Somewhere you want to validate that code under similar scenarios. Here's another example that we've been working with. There's a direct air capture. There are actually folks right here, they're actually Oxypetroleum. They are actually building, if this is going to go ahead, they're planning to build about 50 or 60. It's publicly announced. And this is the reactor that's going in. This article came from New York Times. And they're actually going up it's no man's land in Texas. It's near Odessa, Texas. They're building the plant, which is a direct air capture. To get that 420 ppm, they want to extract CO2 out of that. They want to pump it into the existing pipeline, right? This is another fluidized bed process. It's going on, right? So there's tremendous efforts. So what is the key? What we learned over the 50 years? The wisdom or the things that we learn. What makes the scale-up successful? These are the simplified flow sheet for that. And you don't want to skip to some of these, because, I want to do, clearly management wants to do it in 2 years. But there's a reality versus expectations, right? So you want to make sure you prepare the management to the realistic timeline. Because we know on average it takes 7 to 10 years to scale up a process. Doesn't mean you can compress with all these new tools that we have, but there's a limit. You cannot skip these steps. What are those steps? Well, let's say a chemist proven into the lab scale unit, hey, this process is viable. He hands off to your chemical engineer, say, management says, this looks like very promising. Hey, let's find out Let's optimize this process and prove, let's say, it's a catalytic process. Hey, my catalyst is good enough? How much I need? How much activity deactivation issues? Hey, what are the pressure and temperature I need? You optimize all that. He did that in a little lab scale fixed bed reactor. Now, chemical engineer, we come in here. Now it's our role to take that baton and carry it forward. So this one, hot pilot scale fluidized bed. As we know, small scale fluidized beds are very hard to run. Why? Because they're slug. So anything I produce in that small scale reactor, how do I scale that information to the large scale? And that's a key. That's what you want to understand. You want to get PSRI has a lot of experience in that arena. So you want to include the PSRI in that team, developing that process, in designing and running this. And you want to run this, we recommend at least 10,000 hours, thousands of hours, let me put it that way. Because that's how you learn about your chemistry. You optimize your weight over space velocities. Is my particle ready for reaction in terms of attrition, activation, deactivation cycles? You want to find all those out in this scale because you're talking about a few $1 million investment in here. And that's where you want to find most of the 95% of the answers you want to find out in that scale. Right? And then what's the other valuable? You want to feed that information, start developing that code, the modeling in parallel. You want to feed that information to validate. This is the validation step. It's very, very critical. You want to get that in. And we recommend, I mean, because of the experience, the way they work with us, because that strategic partnership is, if you look at the way they develop the code, they're always utilizing PSRI software, the data to validate some of these things. And I'm sure Peter can talk about that and maybe separate aspect of this, and Sam. So key is that, and then once you get these parameters optimized, next thing is that we recommend go to the demonstration scale. Put in that $20, $40 million investment. It's worth putting that money in and running. Don't skip here to here. Go directly commercial scale. Then you run into certain things. I don't want to name certain process, but a lot of folks, in the fluidization history, there are classical 4 or 5 cases where it failed. Well, you skip certain technology because management was aggressive. They were pushing the engineers. Engineers couldn't resist that. So, well, what happens is you didn't do your homework right. So we have classic failures going that. So proper way of doing it is put that $20, $40 million investment, build that unit, build the right kind of design unit. The way our philosophy is, build the commercial unit first. Okay, what is my first commercial unit looks like? What the size, capacity, throughput. So design that hardware, gas distributors, vessel diameters, you scale the diameter, height, cyclones, dip legs, if it is circulating systems, the standpipes. Design the commercial unit first, come back and do the PDU design. PDU design is a scaled down version of the commercial scale. It has the same kind of hardware as the commercial scale. And this is where you prove this technology works. Right? This is a critical component. You want to at least hundreds to thousands of hours on that unit. And this is where, if you want, right? So this is where you find out, hey, do I have a cooking issues? Do you have any agglomeration issues in the unit? Hey, is there a fouling issue on my distributors? Is there a scale buildup on walls? Is there cyclones fouling? Is the dip legs are getting plugged? These are things you want to find out on that scale. You don't want to find out here because that's going to be that's a billions of dollars investment. And you don't want to make, if we are at this point and you have to fix hardware, we didn't do our homework right. You got to fix those at this scale, right? PDU scale. And you want to do that design, you got to get it design right. And also key, don't go to third-party outfit to build these units. We've seen this over and over repeatedly. That unit should be at least in your control, the environment. That is where you train your engineers. You learn everything about that process. That's your known IP. You want to keep it in your group. You train that engineers, and they are the one going to go up there and start up those units with much more confidence once they've gone through these steps, right? That's our strategy. Key is, again, I'm emphasizing here, CFD simulations. I think right now at this juncture, in my opinion, because of its, the steps it's gone through, wide side distribution I could use in that software, and be able to, and there are steps we recommend going through that to validation steps, right? Like fluidization curve, like Sam was talking about simple angular repose, for those kind of validation tests you do with your powder. Then use these data to validate along the way, and also validate, right? You're trying to pre-predict these things. Hey, how is the modeling doing? Because now we're going to measure these things, and then see if there's synergy, there's a good agreement between those two. If not, fine-tune, right? Same thing. Then you go, don't skip this. Next one is a large-scale cold flow. Remember, even PDU scale, 30, still we're talking something like 8-inch, 12, 8-inch, 6-inch, 8-inch, 10-inch diameter scale. Still wall-dominating region on the hydrodynamics. You want to go to a decent scale where it's no longer, bubbles are freely rising without the influence of walls. And that's the scale. This is where you get, that's where we can help. We have assets, existing assets, so the cost effective of getting that data is get your powder, run in a drag equivalent system, take their hydrodynamic data, and feed that back into the CFD code. And also you have now, with this kinetic, smaller fluidized bed, all the chemistry, now you got to scale up hydrodynamic data. You got a model that's capturing that change in size, the bubble rise velocities, all that mixing patterns, gas-solid contacting efficiency, all those, you characterize this. Now I think your confidence level would be much higher to go to that commercial unit. And this is a now predictive tool. This is now, you have much more confidence using those results, helping us any fine-tuning of the design, say second generation, third generation. Now this would be a very useful tool to give us a direction in which we want to change our hardware. And you've seen that Raj has talked about it. Now John from Shell, talked about it. You can see this can become a tool, nice, useful tool at that point to be able to guide you in optimizing that, fine-tuning the design, right? So with that, I just want, we have a PSRI clan is right here. I just want to say we got a great team at PSRI, so please talk to them if you have any questions and so on. We are, so with that, I'm also looking for a technical director. With the right background, if you happen to have, please talk to me. So with that, all right. Thank you.